Welcome to qnawire.
Okay, so we know the Mach number can be equal to V over C, which is equal to V over square root kRt. So therefore V, which is the velocity, can be equal to Mach number times square root kRt. We know the Mach number is 0.7. The specific heat ratio for the air is 1.4. And the gas constant for the air is 0.06855 British thermal units per pound mass times Rankine. And we know the temperature is given as 320 degrees Fahrenheit, which is about 780 Rankine. So now let's plug in back to the equation to determine the velocity. So the velocity can be equal to 0.7 times square root 1.4 times 0.06855 British thermal units per pound mass times Rankine, and then times 780 Rankine. But remember, we need to convert it to feet per second. So therefore, we need to convert the units, British thermal units per pound mass, to feet squared per second squared under a square root. And the conversion is something like this. So we know 1 British thermal units is about 25,037 feet square per second square. Okay. So eventually this will give us the velocity is about 958 feet per second. So now let's take a look at the pressure, the stagnation pressure. So the stagnation pressure can be equal to P times 1 plus K minus 1 over 2 times MA squared, and then to the power of K over K minus 1. So we know the pressure is given as 25 psia. So now let's plug in back to the equation to determine the stagnation pressure in this case, which is equal to 25 psia multiplied by 1 plus 1.4 minus 1 divided by 2, then times 0.7 squared to the power of 1.4 over 1.4 minus 1. And this will give us the stagnation pressure is about 34.7 psia. So now let's take a look at the stagnation temperature. So the stagnation temperature can be equal to T times 1 plus K minus 1 over 2 times MA squared. So we know the temperature is 320 degrees Fahrenheit, which is 780 Rankine. So now we can plug in back to the equation to determine the temperature, the stagnation temperature, which is equal to 780 Rankine times 1 plus 1.4 minus 1 divided by 2, and then times 0.7 to the power 2. And this will give us the stagnation temperature is about 856 Rankine. So now let's determine the density, the stagnation density of air. So we know the stagnation density of air can be equal to density times the 1 plus K minus 1 over 2 times MA squared to the power of 1 over K minus 1. And we know the density can be expressed as P over RT. So therefore I have rho 0 is equal to P over RT times 1 plus K minus 1 over 2 times MA squared to the power of 1 over K minus 1. So we know the gas constant of the air, which is R here, can be also expressed as 0.3704 psia times phi to the power of 3 per pound mass times Rankine, since we know the units for the pressure is psia in this case. So therefore, we make some little adjustment here. So we use the 0.3704 as the gas constant for the air in this case. So therefore, let's plug in back to the equation to determine the stagnation density, which is equal to 25 psia over 0.3704 psia times phi to the power 3 over pound mass times Rankine, and times the temperature, which is 780 Rankine, and then multiply by 1 plus 1.4 minus 1 divided by 2, and times ma squared, which is 0.7 to the power 2, and then to the power of 1 over k minus 1, which is 1 over 1.4 minus 1. And this will give us the stagnation density is about 0.109 pound mass per feet to the power 3. And these are the answers for this question.